Hello everybody, welcome back to Let's Code a Web App, and today we are going to learn a little bit more about list operations in Lisp. I know in the last video I said we would finally get to coding the web app today, but I forgot that we have a little bit more that we need to go to. So I'm going to open the code for today, which is called lists.lisp. The link will be in the description. Going to open it in Emacs and we will get started. Lisp does stand for list processing and has a lot of very powerful facilities for the manipulation of lists. So let's do this. Let's start up Slime. Excellent. Okay. So before we talk about lists, properly speaking, let's talk about the cons cell. Cons cells in Lisp are written with this dot notation. You use the parentheses, some element, or in fact, let's forego the symbol notation for now. We'll just use numbers. And this is quoted, so it will evaluate to itself, but this means cons cells have two elements. They have a car and a coulter is what they're called, and we'll see why they're called that, but it's just one holds an object or a pointer or a reference to some other object. They both do that. So you can put something in the car, you can put something in the coulter, you can put in numbers, you can put in symbols, and instead of using this notation, you can actually just call the cons function. Cons together, these two quoted symbols here, and that will give you a cons cell. This is sort of the most basic data type, complex data type in Lisp. There are simple data types like integers and floating point numbers and symbols and that kind of thing. But the most foundational complex data type in Lisp is called the cons cell. These create trees. So this is basically a binary tree with two leaves, with a leaf with the symbol A and a leaf with the symbol B. Okay, we can, they're just like any other Lisp data type, so we can assign it to a variable. Oh yes, that is right. I need to do this. Def parameter, violating my own rules. Def parameter cons cell, and then we're going to define cons cell as the variable name cons cell, which let's put these asterisks around it to just sort of distinguish it from the rest of the text. Those are called earmuffs. They're very common for global variables in Lisp. Okay. And cons together, quote A and quote B. The car of this cons cell will be the first element of it, so it's going to be A. The coulter, yes, the coulter of the cons cell will be the second element of it, which will be B. So this is how you build binary trees in Lisp. The binary tree is sort of the most basic data type in Lisp. Just a quick historical note, the reason they're called car and coulter is these used to be machine code instructions on Lisp machines. This stood for the contents of the address register, and this stood for the contents of the decrement register, which was sort of one of those registers that was like the address to the decrement in sort of the old style assembly code and that kind of thing. So if you've seen assembly, this might make a little more sense to you. It's just called car and coulter though. Okay. The thing about binary trees is that it's easy to make linked lists from linked lists from them. So the way that you make a linked list, so the way that you make a binary tree into a linked list is for every left-hand node to be an element of the list, and every right-hand node to be a pointer to another cell. So let's think about how to do that. If the left-hand node is an element, and then the right-hand node is a pointer to another cell, etc., right? So and then in that cell, this is now a new cell. In that cell, the left-hand node is an element, and the right-hand node is a pointer to another cell, right? We can keep doing this until we have to end the list, and they're null terminated. Nil. Nil is the same thing as the empty list. So nil and the empty list is also called nil. It's sort of like null. I don't know why it's in IL. That's how it is in Lisp. But you can see this binary tree got transformed into a linked list. This is list notation, where instead of using dots, we just use these parentheses. That's how you denote a list. It is a linked list underlying, and this is the whole code for it. And you can treat this just like a const cell. If I have a list like this, the car of it will be the first element, and the cdr of it, I think you should think about what it is. What would the cdr of a list be? Well, it's the contents of the right-hand node of the very first cell in this binary tree. Well, what is the contents of the right-hand node? Well, it's another linked list, actually. And so it'll just be the rest of the list. And when we're dealing with lists, one of the things that we can do is instead of saying car and cdr, we say first and rest. Common Lisp doesn't just have the first one. It has the second. We'll get the second element. And the third, we'll get the third element. And it can go all the way up to the 10th. But you can also just use nth 3, A, B, C, D, and that gets the fourth element, because nth is 0 indexed. So it doesn't really quite fit in with the first, second, third paradigm, but it fits in with literally every other language on Earth where things are 0 indexed, except MATLAB. So that is it. That is how to access the elements of a list. You can build lists. You can use the quote notation that I did, which is a little bit more let's say idiomatic for literal lists, but if you need to evaluate elements and then put them into a list or something like that, there's a function called list. So list, the first element will be the addition of 1 and 2, the second will be, divide 3 by 4, the third one could be multiply 5 by 6, and the fourth one can be exponentiate 7 to the 8th power. And this returns a list of all of those things. It evaluates them first. If we had quoted this list, then you would just get a list with a bunch of sublists and that kind of thing. Lists are, for the most part, passed by reference in Lisp. So you have to be very careful about assigning to a list that you get as an argument in your function and that kind of thing. Luckily, Lisp has a mechanism for dealing with this, which is copy list. And so let's see, def parameter our list and list of 1, 2. Okay. So sorry, that was a habit. Okay. Def parameter our list. Okay. So we have this. If we make a function which destructively modify list, let's make a function takes a list as a parameter, and say, so we're going to define this destructively modify list to say set f cdr list and you see So you see, it's passed by reference. If we pass this list into this very poorly designed function that I have here, then it destroys all of my beautiful work of writing out all of those um, integers and does it like that. Oh, but by the way, if you want to go back, unfortunately, just pressing the up key doesn't work like it does on shell. So you go to it and you press the enter key, and that will bring that input down to your current input. That's how you do that in Slime. I should have explained that earlier. Okay, so we do have to be careful about that, but luckily there's a way around this, and it's with the copy list function. Lisp knows that this is a problem, so let's say constructively. Or I really should say non-destructively, but that's just too long. So we say let a new list be copy list list. And now this is the new list, and now we can say setf footer new list 3, and let's return the new list just so it doesn't die. And now we can constructively modify list our list, and that will return that, and we check our list, and it hasn't been disturbed. It hasn't been disturbed. So that's great. Functional programming would say that we shouldn't do things like this very often. We want to think more mathematically. We want to think more about what is the action that we're doing, how can we compose mathematical functions to it. To that end, one very useful function is mapcar. Mapcar applies whatever function you have to the rest of the list. So first of all, the x function raises e to the power of numbers. So 54.598 is e to the power of 4, like the mathematical constant e. So mapcar, so if we wanted to get a bunch of things raised to that, we have to pass in the function. This sharp quote is usually what it's referred to, which is a hash symbol, a single quote, and then the name of the function is how you pass the value of a function that is named by that. If you just put in exp, for instance, it'll think it is a variable that it's trying to reference, and will try to get the value of it and try to use that as a function, which will fail, obviously, in our current environment. If you just do quote exp, then you're passing in a symbol. Hash quote, or sharp quote, as it's usually called, passes in the function referenced by the name, exp. 1, 2, 3, 4, like I have in the code over there, and that gives us this 2.71 is e to the 1, which is e. This is the first few digits of e. This is e squared, e to the third, in floating point arithmetic. Well, let's think about how to do a mapcar. How to define our own, and I've done this. You say, so define our mapcar function list. So the function has to be passed in, the list has to be passed in. If the list is empty, if null list, that's what that means. We can go over the predicates in just a second, but if the list is empty, then return the empty list. We don't have anything else to do. Otherwise, cons together, call the function on the first element of the car of the list. Actually, since we're dealing with lists, let's say first and rest. I usually still just say car and cdr, but this may be a little bit more intuitive. So call the function on the first element of the list, and then recursively call cons it together with a cell, and this will be the rest of our list will now become, we have to recursively call our function on the rest of the list. So let's evaluate this. Let's see if it does what we want. Our mapcar, 1, 2, 3, 4, and we get the same result. We get this. This is not tail recursive. If you notice, this is not tail recursive. I want to go a little bit about predicates. Predicates are functions that return, that semantically speaking, return either true or false. Now, the empty list, or nil, is false. So if I say if nil a, b, then this will always be false. This will always return b. Nil is the only false thing. Anything else is true. If 1, a, b, even though 1 isn't, then it returns A, because 1 is just not null. If the sort of symbol for truth in Lisp is T, which is a self-evaluating symbol, just like nil, it evaluates to itself. Um, and that's how you sort of say true, but often these predicates will just return something other than nil, and that is how they do it. So null list checks to see if it's null. So if it's the empty list, so null nil is true, and null of any other list, any list that isn't equal to the empty list is false. So our list, is that null? No, it isn't. It has a bunch of elements. But if we say set f our list nil, now we'll check for its nullity, and it's true. This is an empty list. This is an empty list. Okay, that's how you check for that. List p takes any object and returns whether it's a list. So list p1 will say false. That isn't a list, that's a number. But list p, the list of just one, is true. These are predicates. Okay. So that's it. So this is our own map car. It's a pretty poor one. It's not tail recursive. As an exercise, I think it would be good for you to think of a tail recursive function. But these are the sort of bare basics of working with lists in common Lisp. I hope you can experiment around with it. You can check out some of the references that I have uploaded in the show notes, and use those to experiment more with lists and see what you can do. There are many more functions that come with Lisp that I did not go over today about lists, but these are the bare minimum, and they will help us get started with the next episode where we will actually start coding on our web app. See you then.